Hi, everyone. This is Prof. K speaking, and today we're going to talk about intermolecular forces and states of matter. So our learning objective for this video will be to be able to explain the relation between the intermolecular forces present within a substance and the temperatures associated with its change in physical states. So before we dive into the full details of this learning objective, I want to define some language that we'll be using throughout this video. So we're going to be talking about particles interacting, and in the case of this video, particles can mean an atom, a molecule, an ion, these interacting with each other in different amounts. It just refers to something that's participating in these interactions. Intermolecular forces are the various forces of attraction that may exist between the atoms and molecules of a substance. So this is just the label we have for how these atoms and molecules interact with each other and what sort of forces they experience, which is maybe something you hear more in a physics course, which is what is the force acting on some object? The atoms and molecules are applying forces to each other because they're interacting. And so we're going to talk about what those forces look like, how strong they are, and what they can mean about our various systems. And then when we also are going to talk about the kinetic energy of particles, which is how much energy that a particle possesses because it is in motion. And so in Chem 14 and maybe in other courses, you may have seen that the kinetic energy is equal to 1/2 the mass of what's moving and then the velocity of what's moving squared. And so what this is saying is that our molecules or our particles contain some energy because they're in motion. And that energy is called a kinetic energy. And so I want you to think back as to what do we use to measure kinetic energy of molecules? Or what is it that we like to talk about here? So I'll give you a few seconds to think about this. But hopefully you'll identify that the way that we measure kinetic energy is via temperature. And so we measure the kinetic energy of molecules by measuring their temperature. And so that will help us as we start to think about how phases potentially change as we change the temperature of a system or as we change something else about our system. And so to start off, how do we know what is a solid, a liquid, or a gas? And so when faced with a picture like this, and if I tell you one's a solid, one's a liquid, and one's a gas, you might be able to identify that this beaker on the left is a solid, it's got these closely packed particles, and it's not sort of filling its container. It's just sort of sitting in this little chunk at the bottom. Our liquid, on the other hand, potentially is this middle one where they're touching and they're filling their container, but it's not as closely packed or organized as our solid. And then over here on the right, we have our gas, which is just a couple molecules that are bouncing around in this beaker. And they're not really touching each other, and they're kind of going wherever they want in the beaker. And so you could hopefully label one as a solid, one as a liquid, and one as a gas, if you're told sort of that they look like this. And the next question we might want to ask is, which of these has the greatest kinetic energy? And so now we're thinking about energy in motion. And so if you look at this, you might say, I don't see any arrows representing motion in my solid. So my solid probably doesn't have a whole lot of kinetic energy. And it is the case that these atoms might be vibrating a tiny bit, but maybe we can't even see that they're vibrating because it's so small. Our liquid, on the other hand, you can see some of these lines indicating that they're sort of gently bouncing off each other. So there's some amount of motion here that's visible and that we can sort of see as kinetic energy. So our liquid has more kinetic energy than our solid, and our gas has even more kinetic energy. It's bouncing around even more, and it's able to sort of exist in more states as it's moving around in this container. And so if we look at our kinetic energy as we move across this, we increase our kinetic energy as we potentially increase our temperature, and we can use temperature to move between a solid, a liquid, and a gas. And so A common example of this is ice melting. So if you have solid ice, you can increase the temperature, you can input some heat into the system, and it will melt and turn into a liquid. And that liquid has more kinetic energy than that solid had. And if you continue to heat it, if you continue to put energy into the system, you can raise the temperature and produce a gas. And so these are the different states and how we talk about them in terms of kinetic energy. But how does that relate to the concept of intermolecular forces? Or which one has stronger intermolecular forces? And so if we're talking about interactions and attractive forces here, in a gas, they're not interacting to that much, and they're mostly just sort of bouncing past each other. On the other hand, a solid is really closely interacting with the atoms that it's next to. And so when we look at this plot, we actually see that increasing intermolecular forces go the other direction as you move from a gas, a liquid, or a solid. And what this means is that if you want to go from a solid to a liquid, you have to add heat and break up these attractive intermolecular forces that are happening in the solid. This solid's happy as is, it's interacting with its friends, it's in a sort of a stable configuration, and it doesn't have a lot of kinetic energy, but it has a lot of strong intermolecular forces. As you move to the liquid, you increase the kinetic energy, and you're overcoming some of these intermolecular forces to form this liquid. And as you continue to heat this compound and raise its temperature, you further reduce the effect of the intermolecular forces, and they interact with each other less. And so another way that we can think about this is if I had two different samples, one that has very strong intermolecular forces as a solid, and one that had weaker intermolecular forces as a solid, it would be easier to melt the solid that has fewer intermolecular forces because there's less holding the solid together. So the melting point of that solid is going to be lower if its intermolecular forces are lower. And the same holds for a liquid. If a liquid has weaker intermolecular forces, it's easier to boil it. And so we can use the concept of intermolecular forces to talk about these processes or phase changes as we move from solids to liquids to gases. And so we're going to continue to talk about this in greater detail as we move through this section, but this is just sort of a warm-up where we look at these images and we think about what's happening in these systems. And so to summarize the states of these materials that we're interested in moving between in this section, we have a solid which has particles that are tightly packed together and are often arranged in a regular pattern. And so this is like the image on the last slide, where they're sort of neatly stacked and interacting nicely. A liquid, it has particles that are close together, but maybe they don't have a regular arrangement with each other. They're sort of moving past and gently touching each other. The gas, the particles are farther apart and they have no regular arrangements. They're just sort of bouncing wherever they want in whatever container they're in. And so I keep talking about our particles moving, which is a little bit different than what we've discussed in the prior course, Chem 14, or which you may have seen in other chemistry courses. And so now we're really looking at how are our individual particles vibrating. And so our solid, if our particles are vibrating, they're mostly doing it close to their position, and they usually don't slide past each other. There are some exceptions in higher level chemistry courses that we talk about, but for the most part, we think about solid particles as pretty stable in position. Liquids, however, can move past each other and they stay in close contact, but they're free to sort of wander about the liquid as they please. And gases, we think about as moving pretty independently as particles, but occasionally colliding into each other. And we can talk about how sort of thinking about gases this way can affect things like the ideal gas law, which we introduced in Chem 14, and we'll sort of go into more detail there. But this is just sort of specifically thinking about how we talk about particles and motions in different states, and how, once again, that helps us move from solids to liquids and gases. And so if you increase the kinetic energy of your temperature, or you cause the particles to vibrate more and more, you overcome these intermolecular forces and you can melt your solid, or you can boil your liquid into a gas, and sort of we can move back and forth across this chart. And in the next video, we'll get more specific about what intermolecular forces actually are and why they are controlling our particles the way that they are. And then in the next video, we'll start to talk more about how we can actually describe the way that we change phases. And so we're going to spend a lot of time working in this area, but this video is just supposed to get you started and get you thinking about phases and intermolecular forces so that we can move forward to slightly more in-depth discussion of these topics.